cover the theory of the expansion of solids, liquids, and gases. The delta L is equal to alpha L initial delta T gives us the equation for the linear expansion of a metal, or it could be any other material, the linear expansion in the linear direction. Delta V is beta V initial delta T gives us the volume expansion of a liquid or a gas, right? So what is representing? This is in meters. This is also in meters. This is Celsius, right? So alpha is the coefficient of linear expansion. Coefficient of linear expansion. And the units of this is going to be 1 over Celsius, right? 1 over Celsius, which will cancel this Celsius, and then meter will equal meter. Let's give the coefficients of linear expansion of different materials. We have the alpha of aluminum, the coefficient of linear expansion of aluminum, 24 times 10 to the minus 6. Now notice that these are not big numbers. So the initial length of the aluminum needs to be very, very large in order for the change in length of the metal to be very large, right? To be noticeable. So for the most part, the expansion of metals is not noticeable unless the metal itself is long to begin with, right? Alpha of the brass is going to be 19 times 10 to the minus 6. Alpha of copper, 17 times 10 to the minus 6. And then alpha glass, 9 times 10 to the minus 6. So even non-metals expand. Basically, the reason that materials expand when heated is that the molecules start vibrating faster and pushing on each other more, and they spread out, right? Because their kinetic energy increases, and then their temperature increases, and it causes their space between them to expand, right? Lead is equal to 29 times 10 to the minus 6. So far from these, lead is the highest, right? And then glass is the smallest. And then steel is 11 times 10 to the minus 6. 11 times 10 to the minus 6. So from the metals, steel is the smallest, right? 24, 19, 17, 29. Yeah, definitely for the metals, the steel is the smallest. And then we have concrete too. Concrete is 12 times 10 to the minus 6. So even the concrete, the tiles, everything that you have in your house outside on the ground, they all will expand, and you must put a little space between different tiles so that when they expand, they don't crack, right? Fill up that space with a material that we call grout, right? In order for the tiles not to crack when they expand, right? Talk about the expansion of liquids, right? Delta V. So the volume expansion of a liquid, delta V, depends on the initial volume of the liquid or gas and the change in temperature, and then the constant is the constant of volume expansion, right? Beta. Okay, so beta is also going to be in units of 1 over Celsius, and here is the beta of different liquids. We have, and we see here that this is the gasoline is the most from this list, and alcohol is the least from this list. Least. And this is the most. And then we have a couple betas of the gases. Beta of air is going to be 3.67 times 10 to the minus 3. Now there's a little note that is given in the table, and it says gases do not have specific value for the volume expansion coefficient because the amount of expansion of the gas depends on the type of process through which the gas is taken. The value given here assumes that the gas undergoes an expansion at constant pressure, right? So we will learn about this more when we're going through thermodynamics. There's an isobaric process, isothermal process, adiabatic process for gases, right? So this process, beta, is assuming constant pressure, which means it is assuming an isobaric process, right? And then they also give the same beta of helium for an isobaric process, beta of helium, and that's going to be 3.6665 times 10 to the minus 3. So very similar. That us derive the expansion of a solid if it is expanding in 2 dimensions or 3 dimensions, right? What will the equation be? So imagine the solid is a tile, and it's a tile on the ground, and it is expanding in 2 dimensions, right? Right? Both the length and the width are going to expand. So the length is going to expand in amount delta L, and the width is going to expand in amount delta W, right? Delta W is going to be smaller because the width is smaller, right? The amount of expansion depends on the original length, so the width expands less than the length does, right? So then what's the new area? A final is going to be equal to L plus delta L, right? The initial length, so we can call this L initial, W initial, L initial plus delta L times width initial plus delta W. Right? Then we multiply this in L initial width initial plus L initial delta W plus delta L width initial plus delta L delta W. L initial width initial is the initial area, right? A initial. And then delta W is going to be alpha W initial delta T, right? So it's going to be alpha W initial delta T, delta L W initial, and then we could put delta L as alpha L initial delta T, alpha L initial delta T, and then width initial plus delta W delta L, right? So then what's going to happen here? A final minus A initial is delta A. It's the amount by which the area increased, right? Delta A. So we can, I'm subtracting here A initial from this. And then I have here L initial, W initial, that's the initial area, right? So you have here alpha A initial delta T plus, then you have another one of these L initial, W initial, so you again get the initial area, so you get alpha A initial delta T plus delta W delta L. Then we're going to say delta A is equal to, we can add these two, 2 alpha A initial delta T plus delta W plus delta L. And then you're going to get delta A is going to be 2 alpha A initial delta T plus then you have alpha squared, W initial, L initial is the initial area, delta T squared. What we're going to say is that this alpha squared is much smaller than alpha because, as you saw, alphas are all usually of the order of 10 to the minus 5, 10 to the minus 6, right? When you have 10 to the minus 6 squared, you're going to get 10 to the minus 12. So this component of the equation is going to be very, very negligible compared to this component of the equation. So we can get rid of this. And then, therefore, this is going to be the equation for how the area changes of the area of the tile. So we can write this equation here. dA is going to be 2 alpha A initial delta T, right? So it depends on the original area of the material, and then 2 times the alpha delta T. So we can use the same alpha as for linear expansion, but we're just now doubling it, right? Then we can come up for a solid 3-dimensional object. We can say L, W, and then H. Same argument, right? Delta V, what is that equation going to be? Then distribute this in, we have V final, L initial, W initial, H initial, plus L initial, W initial, delta H, plus, then multiply this by this, 2 alpha A initial, H initial, delta T, plus 2 alpha A initial, delta initial, and delta T, right? So V final is equal to what? L initial, W initial, H initial is the initial volume, right? Then we put here L initial, W initial, delta H is equal to alpha H initial, delta T. So wherever we have a delta H, we're going to use the alpha H initial, delta T. Then we have here 2 alpha A initial, H initial is the initial volume, plus, then we have here 2 alpha A initial, and then delta H is going to be alpha H initial delta T times delta T. Right? So then what are we going to have here? V final is going to equal V initial plus L initial, W initial, H initial is the initial volume. So alpha V initial delta T plus 2 alpha V initial delta T plus you have 2 alpha squared A initial, H initial is the initial volume, and then delta T squared. Well, for the same reason that we did before, alpha squared is going to be much smaller than any of the alphas, and then we can also cancel this and make it 0. So then we have 2 alpha V initial and another alpha V initial. So we have V final minus V initial is equal to 3 alpha V initial delta T, and then the V final minus V initial is equal to delta V. So then my equation is going to be, object is expanding linearly, depends on 1 alpha. In 2 dimensions is 2 alpha, and then in 3 dimensions it is 3 times alpha. So this equation works for solids, and then the other equation that we have, delta V, is beta V initial delta T, works for liquids and gases. Then we will do some examples of these. Thank you very much.